a lot is known about what happens in even non-interactive topological systems like anomalous topological insulators and in these interesting things, whereas that's much less known for interactive topological systems. The other point, of course, is that this might point towards a different way to try to reach Majorana zero modes in quantum simulators. Okay, so let me start with a bit of introduction. So first of all, what is the torque? We have already actually seen it in previous talks. The name was the lattice gauge theory, and it describes two-level systems living on the bonds of a square lattice, and all these spins interact only with four-body interactions, which are of two types. So we have plaquette terms, which are the product of sigma z Pauli matrices, and then we have vertex terms, which are instead products of sigma x Pauli matrices. And we might have different coefficients. So before, what we saw before was that in the Z2 lattice gauge theory, the four-body sigma x term will correspond to the Gauss law constraint, which here is included as an energetic penalty also into the Hamiltonian. So the key features of this model is that it's exactly solvable. And the reason is that all these four-body interactions commute with each other, essentially because ZZ commutes with XX, and all plaquettes and vertices share, at least actually share exactly two spins. Okay, so how do anyons appear in this model? So if we think of the ground state, since the model is exactly solvable, the ground state needs to satisfy the constraint that the expectation value of both plaquette and vertex operators is exactly equal to 1. However, we could have violations of these constraints, so plaquettes or vertices, where the expectation value is equal to -1. And in this case, we talk about having an electric charge, for instance, for the violation of a vertex constraint, or a magnetic flux for the plaquette constraint. And how can we actually achieve these violations? This is pretty easy. So the idea is that if we have, for instance, a single spin flip, like a sigma x operator, this anti-commutes with the surrounding plaquette as Z terms. And therefore, if you think of the expectation value, you just anti-commute your x operators through the plaquette terms, and you can convince yourself easily that this leads to a violation of the plaquette expression. All right, so actually in the abelian angular torque are core, so we have the vacuum, so the case of no violations, the E and M particles that I just introduced, and the composite particles which can be obtained through a combined violation. And in the following, I will actually, so in principle, it's arbitrary to choose as fundamental particles E and M, and psi as the composite particles, but in principle, and this is what we'll do later, I will take psi and E as the fundamental particles and M as the composite. Okay, so why are they anyons? So if I just take E particles and break them with each other, they actually behave like bosons. The same is true for M, whereas the psi particles behave like fermions. Why does this happen? The reason is that if we take an E particle and drag it around an M particle, again, because of the anticommutativity of X and Z, this leads to an accumulation of a minus sign, so a pi phase in the wave function. So we can interpret this by saying that the E particles see the M particles as pi fluxes, or the other way around. And the same is true for the psi. So when a fermion encircles one of the bosons, it will acquire a pi phase. And from now on, whenever I will say fermion, I will refer to psi. Whenever I will say boson, I will refer to actually the E particle. All right, so now I introduced my abelian model, and I start to wonder, what are the ingredients that I'm actually missing to be able to promote this to non-abelian system? For this, I picked up the most simple model probably one can think of, which hosts non-abelian Ising areas for my Majorana zero modes, which I just photographed from the recent book of Sachtel. And okay, this model has two ingredients. So again, a Z2 gauge field, which will be our toric code part, and some fermions, and the two are coupled with each other. So let's look at the fermions. The fermions have some chemical potential, they can tunnel in the lattice, and the important ingredient is that they can pair with each other, so they're superconducting, and they pair in so-called P plus I plus C, which for us just means that the pairing along the X direction is real, the pairing along the Y direction is purely imaginary. Okay, all these ingredients, when put together, okay, and of course, there's the coupling of the fermions with the Z2 field, which allows us to give the behavior, and it means that we can have vortices in the system. So, okay, these ingredients together allow for existence of non-abelian angles, which are the vortices in this model, so excitations of the Z2 class, of Z2 field. And they're non-abelian because they can, when combined with each other, they can fuse either to the right or to further. But okay, so without entering now so much the details of this, I just want to point out that we have these three ingredients that we need. So the coupling of the fermions to the H field. We have the fermions that need to be superconducting, and to be superconducting in P plus IP symmetry. P plus IP symmetry is needed because we need some non-trivial topology for these fermions. So I look back at the toric code now, and I wonder which of these ingredients are actually there. So we saw that the E and the M particles see each other as pi fluxes. So we could interpret one of them as a vortex for the other, as a Z2 vortex for the other. On the other hand, the fermion, the emerging fermion, what I call it psi, or in the toric code, is just there. It's based there, it doesn't move. And so certainly it's not superconducting, and it's not superconducting with non-trivial topology. So what I will try to do next is to use the Fouquet drive to try to remedy for this and to be able to imprint on the toric code these missing ingredients. How can I do that? So we saw before that the creation of a double violation is obtained by an operator that looks like this. So a ZX coupling. And so if there are no fermions, I will create a pair. If there are two fermions, I will annihilate them. If there is one fermion, this operator will make it travel throughout the lattice. So I, let's say, enrich my toric code model by adding just these terms with some prefactor, which will be different along the X and Y direction. We can already imagine why I'm doing this, because in the end, we want to have different pairing. I want to have this P-wave pairing. Okay, so this is my model. But now, okay, it's hard to understand from the spins, from the perspective of the spins and this complex toric code, how the excitations actually behave. And a way, so a formalism that can help us in this is some mapping that was worked out, for instance, in this paper by Sherrod and Solomon, which essentially maps the spins to operators that describes the quantified excitation. So something similar to picture, but in our case, it needs to take into account that we have multiple particle types in this theory. And okay, don't discuss the details of the mapping. The mapping is not really immediate, but it's somewhat sort of Jordan-Bittner transformation. And essentially what one arrives at is that my toric code gets mapped to this model. So a model where I have my fermions, which have a certain, okay, first of all, the model maps each plaquette for fermion. So this is what this picture shows. So I have my spin model here, and then I can just map it to a model of fermions living on the plaquettes, whereas the vortices, the E particles, will live on the vertices. And okay, so I look at the ingredients I had. So okay, the chemical potential here is just the energy that I had in the toric code to create a double violation. So this will be essentially related to the couplings I had in the initial model. But then I have the drive introduces these terms, and like we expected before, we already said that the drive can both create pairs and make individual fermion standards. So we have something like this with some coupling, some tunneling term, and some pairing, plus the coupling to the E bosons. So what is this doing? This is essentially just reproducing this pi flux situation, but if I take the fermion and braid it around the flux, I will get a pi phase. Okay, so we are close to getting the model we want, but we still have a problem. Namely, the fermions now are, so if the drive is weak, the pairing terms will become more present. On the other hand, if I crank up the drive, the pairing will still have a real coupling. So I cannot achieve this P plus IP pairing symmetry that I would like to obtain. In other words, if I just get a static drive, so if this D of R would just be a constant, and I will be adding fluctuations of the emergent fermion, this wouldn't give me the physics I'm looking at for. To remedy for this, I then introduce a modulation. So I use Fouquet engineering. So it's known, of course, that Fouquet engineering can be used to bring non-trivial topology, but in this case, it will not be applied to the realization of an artificial gauge flux, but rather to artificial imaginary pairing. And how does this work? So I have again my term here, and I choose these driving functions who have two frequencies, so the zero frequency component which will just keep the resonant tunneling term, and then I modulated the one component of frequency omega. How do I choose this omega? I choose it to be almost resonant with the energy needed to create a pair. I say almost because in the end, the tuning from resonant will give me an effective chemical potential for this pair fermions. And I allow for different phases along the x and the y direction. So what's the situation here? If I would just forget about the modulated part, because the mu psi would be larger as compared to the driving, the pairing would be off resonant. But I restored my modulation with a gain advantage that I can interface. And this is the usual photon assisted tunneling picture in a way, only here applied to the fermion pairing rather than tunneling. So, okay, with this, one can do usual tricks in flow engineering, so like frequency expansions and such things, and compute what's the result of this kind of UI. And by choosing simpler like shaping, so a phase, for instance, 0 and 1 x direction and pi alpha in the y direction, this will end up flow engineering exactly this pairing, this p plus ip pairing. So a real pairing on the x direction and an imaginary pairing in the y direction. Okay, now, of course, this will now be technical, but I want to I constructed my flow model. Now the question is, does it actually have all the features that I expect the non-abelian system to have? So to do this, one thing that I didn't stress is that this construction, in the end, maps to, let me just go back one slide. This construction in this quasi-particle mapping maps the toric code into a model of static E bosons, because my drive is constructed such that it only drives fermions. And for the fermions, it leads to a quadratic model. So something that I can solve very, very efficiently mapped. And in this way, I can study the Lagrangian spectrum of these fermions and check whether we do have properties that we expect for the system. So first thing that we can check is the topological degeneracy. So I put my system on a torus. For the toric code, it's known that the system then should have 4 degenerate ground states, whereas for easy topological order, in the abelian case, we expect to have 3. And here, essentially, I compute this degeneracy by considering different ground boundary conditions for the torus, which amount to choosing different topological sectors. And what one finds is that for toric codes, so you see, what you should see in this plot is simply that the difference between the lowest one of the degenerate ground states and the others is going down quickly. There are 2 separate curves. I will therefore just forget about the last line. I will maybe comment on it in 1 second. And so we see that this goes down exponentially with the system size. And what we find is that since in the toric code, you saw at the beginning that if I flip one spin, I always violate 2 plaquettes. So I always can create only an even number of particles. Essentially, what I find is that the 4 degenerate ground states of the toric code reduce to 3 because one of them becomes unphysical in the sense that it describes an odd number of fermions, which I cannot create in the toric code. And okay, so the topological degeneracy is verified. Next step, I have to see if all this locate script that I did is actually achieving this non-trivial topology. To do that, I place my system on a cylinder and just check whether I do have edge modes. And this is what I'm showing here, which is also well reproduced. Again, what I'm doing here is recomputing, propagating the time evolution for the fermions, for the Floquet degenerate Hamiltonian, extract the Floquet degenerate Hamiltonian, and check the quasi-energy spectrum. Okay, in the frequency. All right, next step is, okay, this is sort of the appetizer. Now the question is, do we actually get non-abelian statistics? So first of all, let's see what happens if I insert 2 E bosons in the system, which should behave like vortices in this P-wave superconductor. I again compute the Lagrangian spectrum as a function of my gravity. So what we see is, first of all, that in high frequency, so if I lower my amplitude and keep the frequency fixed, I'm entering more and more into the very high frequency regime. And we see that for high frequencies, we do get perfectly our Miranda zero modes, which are also exponentially localized at the vortices, as they are expected to be. Then, as I crank up the driving amplitude, the features are not completely lost, but we see the formation of high modes. So we start to see this anomalous bouquet regime when we depart from the high frequency description. Okay. At this point, the question is, okay, what about the non-linear statistics? So verifying that grading these anyons actually prints any transformation would be numerically quite complicated, but we can use a proxy for that. And the idea is that one can, so from the theory of decreasing anyons, we know that if we create two vortices from the vacuum or in the topological sector of the fermion, what we obtain is that the grading should have different phases. So in other words, in practice, this means for my system on the torus, if I choose anti-periodic boundary conditions on both directions, only one direction, and then in the two cases I create two vortices, their exchange should depend on this topological sector. So how we extract this abelian part of the exchange phase? There is a well-known protocol which tells us to essentially do a sequence of displacements of our anyons, which differ by an exchange of the anyons. So, for example, here I first lower one anion, then pass the second through the first. Then I do a different path where the sequence of positions is the same, only by range. No? I first displace the central anion, then I break down the second one. Okay, if we do this, the difference of the phase acquired in these two processes should give me exactly the exchange phase. How do I do this in practice? Essentially, I take my system, I introduce two vortices. This will change some parameters of my Bogoliubov Hamiltonian. I can then construct the ground state in BCS form. Floquet ground state meaning I'm in high frequency, so I can have well separated Floquet copies, and I can be inside one copy of ground state. Once I have this Floquet BCS ground state, I can compute it for different vortex positions, and just extract the Barry phase accumulated in this movement by considering the expectation value of the tandem operator. So this T operator will just be the operator that takes this vortex and drags it down. Since which will have also a Fermat component, but I don't want to bother with all the technical details. So this is what one thinks. So the prediction for isotopological order is that in the vacuum sector, so if I create two vortices from the vacuum, the exchange phase should be minus pi/8. If I create it in the cyclone sector, then the phase should be 3 pi/8. And the reason, the fact that these two exchange phases differ by a pi-half phase is exactly a signature of non-abelian physics. So also in this case, then I compute my Floquet Hamiltonian and construct the sequence of the KBCS ground states and extract the exchange phases. And one obtains is that as the system size increases from 10 to 20 in the sense of 10 by 10 or 20 by 20 square lattice torus, then we see how in the vacuum sector and the fermion sector, the exchange phases exactly converge towards the predicted expected values, which are here just given in units of pi/8. And as we instead start to crank up, so again, here, if I go, what I have in the x-axis is the driving amplitude. So if I reduce the driving amplitude, I go to a high frequency regime where I expect what is theory that I showed at the beginning to be more valid. And instead of the crank up the driving amplitude, I still start to see the departure from the screen. All right, so summarizing, what I told you until now was to show you that one can convert the median anion system to a non-abelian anion one by means of a Bouquet modulation. And I try to explain what's the essential mechanism behind this conversion by using this construction with the torque. So the essential idea is that in these 2D systems, anions will be localized in the absence of perturbations, and we can drag them around with local control. And the second ingredient is that something that we know very well, that a Bouquet drive can create trivial topology on the system. Okay, this is you can find more details in the reference for this paper. And I want to just, I think I have a couple of minutes for questions. So I want to just discuss potential outlook about this. So the first thing is moving away from what I would call the kind of exactly solvable one. So now this construction is really the dock in a way that I told you before. So construct the drive, essentially it doesn't touch the vortex part, and that it doesn't introduce thermal interactions. So in this way, you can able to do all the simulations very efficiently, also for large systems, which wouldn't be the case. The question is, if I try to simplify, for instance, the drive, for example, I just plug in a single drive rather than this ZX coupling, can I still keep this kind of physics, or would I break down? The second question is, of course, now this was all abstract. So you could say, what about the torque code? That's already force-feed interactions. That's probably feasible, but actually we have a proposal how to realize the okay engineering, the references, we find it. But actually what I want to say is that the torque code may look a bit ugly, but actually there are real systems which even have ugly versions of the torque code. So for example, a couple of, now I think 3 years ago, Michel looking, they realized this spin liquids of Rydberg excitations constrained by Rydberg. So they put Rydberg atoms on the bonds of a Riemann lattice, so it's called a Ruby lattice. And essentially the presence of one excitation blocks because of Rydberg blockade integration of nearby sites. And essentially it was worked out recently, for instance, in this paper, that this model with the Rydberg blockade up to a certain number of Lewis neighbors can be mapped exactly for torque code with 4, 3, and 6 bound interactions. So my point here is that maybe this could be an interesting platform where we explore these ideas by introducing tries to drive the fermionic excitations of this model. And with this, I thank you very much for your attention and questions.
Thanks about Francesco. So we are now open for questions. Let's see one at the back here. You start.
Okay. Yeah, thanks, Francesco. Actually, I just want to know something like this. So we had that you started with like a billion system. Then you did a prototype, right? And the whole idea that you wanted to do some topological symmetry class superconductor, like some topological superconductor. And then once you add that class, then this billion anion was able to acquire some U2. Was it this the case for the U2? So it was in the non-available, was it this U2? So I was wondering, like, what was this non-available? Was it U2? And
so the class of the fermions in terms of in terms of like the classification in terms of
so in terms of like you said like the non-available is unitary, right? Like once they go around, so they do like U2, I believe. So I'm just wanting to understand well, and is it connected to Z2 ratio, which you are talking about?
Okay, so the non-abelian,
and you know, which you could get because of the fluke.
Yeah, that's confusing area. So I think true, but this refers to our
so the easy one.
So okay, so essentially the non-abelianity comes from the fact that if you break further, for example, if you break these vortices, they can, for example, you have 3 vortices and 2 of them fuse to the identity. If you take the third and break them around the first two, this can actually make them fuse into I said the vacuum before, now the fermion. So we can change the topological sector where 2 of them fuse. And so this we can describe with a liter matrix. And in the end, essentially, for example, if you have 4 vortices, you will have a 2-state system that you can control by just breaking these vortices on top of each other and performing literally rotations, like qubit rotations inside and inside.
Okay, so this is what I was. Yes.
Okay. Okay.
Yes. Okay.
Yes. One more question then. So can you comment on the detrimental effects you think here? Like you have like many body from a system and then you were driving it. Do you expect it to go to the chemistry state and yes, and more time scales to apply, etc.
Yes. So actually, so because of this construction, that in the end is basically keeping. So we have again the basic model is of course interacting, but it would be it's exactly solvable. When I introduce the drive, it's not exactly solvable anymore. But through this mapping, you see that it ends up into a system where we have a static background distribution of these vortices, which don't move, so we don't care what we are driving on the fermions. But since in the end the mapping ends up with a quadratic model for the fermions, by construction the model shouldn't heat up to infinite temperature. Then of course, if one breaks a bit any of the symmetries in the drive, course, this is one has to see what happens, and the system will probably heat up very quickly, but in this construction, there's no heat, it's really just mapping of the.
Any further questions, comments? Okay, so thank you very much.